We set our sights on the farthest target, Proxima Centauri, 4.25 light-years away. We dreamed of setting out to solve the secrets of the universe. But we found the greatest and most terrifying limit not among the stars, but within the traveller. The mere fact that Mars's 38% gravity began to dissolve our bones was a warning. The harsh reality that the radiation of space saw our every cell as a bullseye was a bitter truth. It became clear that even the most advanced starship is meaningless if the human inside slowly breaks down. But what if there's a way to save the body by bending time? If you want to understand how an astronaut's body can be both their greatest enemy and their greatest hope, like and subscribe. Because the answers are not where you think. We begin. For years, we thought the greatest limit to space travel was technology. We believed we could reach the stars with bigger rockets, more powerful engines, and more fuel. This dream carried humanity into orbit, then to the moon, and even to the outermost edges of the solar system with robotic probes. But with every step, we faced a deeper and more unsettling truth. The real limit wasn't in the metal, the fuel, or the equations. The limit was the traveller, our own bodies. And now we understand that to extend a human lifespan to the stars, we must first understand just how fragile that life is, in the face of the universe's most brutal rules. This is why we must first relearn the concept of scale, because the word distance as we use it on Earth loses its meaning in the void of space. Our minds understand kilometers, but we cannot intuitively grasp the speed of light and the distances it travels. The Moon, the farthest world humanity has set foot on, is just 1.3 light-seconds away. That's so close that the Apollo astronauts' journey took only a few days. A distance like crosses in less than a calm breath. Mars changes things. Depending on the planet's alignment, Mars can be anywhere from a few light minutes to over 20 light minutes away. This means an astronaut on Mars can never have a real-time conversation with Earth. Every word, a delayed message, drifting through the orbital silence. But that's not the real shock. All of this is still our neighbourhood, the warm, gravitational confines of the solar system. The true reality shock begins when we look to the nearest neighbouring star, Proxima Centauri. Because it is 4.25 light-years away, not light minutes, not light hours, but light years. Even the fastest message nature allows takes more than 4 years to get there. At our current technological level, this scale means the journey would take tens of thousands of years. Therefore, the question of interstellar travel is not just, how do we go faster? The real question is, what is a human lifetime next to this distance? So how could this be possible? If technology is so inadequate, why do we still dream? Because the problem isn't just about building better engines. It's about overcoming the brutal reality of one of physics' most fundamental equations. This is known as the rocket equation, and it has a simple but unforgiving rule. How much a rocket can accelerate depends on its exhaust velocity and the ratio of its mass when full of fuel to when it's empty. But there's a logarithmic trap. Adding more fuel for more speed also makes the rocket itself heavier. To push that weight, you need even more fuel. After a certain point, brute force defeats itself. This is why rockets shed their parts in stages just to get into orbit. But there's a physical law even more fundamental than this equation. Kinetic energy. Kinetic energy increases with the square of velocity. This means that doubling the speed requires 4 times the energy, and increasing it tenfold requires about 100 times more energy. Even just 1% of the speed of light, 3,000 kilometers per second, is a fantastic speed for our current vehicles, and even at this speed, it would take 425 years to reach Proxima Centauri. The minimum speed required to make this journey in a human lifetime is about 10% of the speed of light. This reduces the journey to 43 years. But the energy required to reach that speed is a decision not for a single vehicle, but for an entire technological civilization. This is why the phrase, "just go faster," is the most innocent misconception in space travel. A starship is not a car with a bigger engine. It is a system that must pay for every increment of speed with the most ruthless mathematics of energy. But Let's say we solve this energy problem. Let's say one day our civilization finds the power to accelerate a starship to 10% of the speed of light. It is then that we encounter a much deeper and more personal wall, biology, because the passenger is not a machine. It is a warm, wet, electrically alive, and chemically restless being. The human body is an instrument, finely tuned by a planet. It has evolved for a specific atmospheric pressure, a specific gravity, a magnetic shield, and a daily rhythm. The moment you step into a spaceship, your body enters a world where all those assumptions disappear, and it immediately begins to adapt. But adaptation in space does not mean the same thing as health on Earth. Without gravity, your leg and back muscles weaken because they are no longer carrying a load. Your bones, especially the weight-bearing ones, lose mineral density because the skeleton is no longer stressed as it is on Earth. The body slowly rewrites itself for a world where standing is unnecessary. Fluids shift towards your head, puffing up your face and causing vision problems in some astronauts. But the most unforgiving of all is radiation. Beyond Earth's magnetic shield, you're exposed to both particle storms from the sun and high-energy cosmic rays from the depths of the galaxy. This is a bombardment that cannot be stopped with a simple shield. For a trip to the moon, this is a manageable risk. For a trip to Mars, it is one of the main design problems. But for an interstellar journey lasting decades, it is a survival equation that defines the very architecture of the ship. We understand that to go to the stars, we must overcome 3 colossal walls: the mind-boggling scale of distance, the physical limit of energy required for motion, and the struggle of the human body to survive the journey. Each of these is an obstacle large enough to stop a civilization in its tracks. These 3 walls clearly show why interstellar travel is still a dream. But, despite this dark picture, physics offers an unexpected door. Because one of the strangest secrets of the universe is that motion itself can bend time. So what if our greatest obstacle, time, could actually be our greatest ally? And it is at this exact point that one of the strangest yet most powerful secrets of the universe takes the stage: special relativity. Because Einstein taught us that time is not a universal river flowing the same for everyone. Time is part of a fabric called space-time, and it is personal, depending on how fast you move through that fabric. This means that a human lifetime is no longer a fixed unit of measurement. It has 2 different meanings. The first meaning is the lifetime measured by the clocks of those who remain on Earth. This clock is ruthless and fixed, because nothing with mass can reach or exceed the speed of light. So in an 80-year Earth lifetime, no ship can travel farther than 80 light years. Even at an extraordinary speed like 50% of the speed of light, the distance you would cover in 80 years is about 40 light years. This means a bubble containing dozens, maybe hundreds of star systems. But this bubble is still a microscopic dot inside the 100,000 light-year wide Milky Way galaxy. Even at 90% of the speed of light, an 80-year Earth time window takes you at most 72 light years. This is the cold hard math of the journey. According to Earth's frame of reference, a single lifetime can never encompass the entire galaxy. But the real revolution doesn't start here. The revolution begins when we look at the clock of the passenger on the ship, because that clock runs differently than the clocks on Earth. This second meaning is the proper time measured by the passenger's own body, their own biology. Special relativity says that at high speeds, time slows down. This is called time dilation. The faster the ship goes, the slower time on the ship flows relative to Earth. When you reach 99% of the speed of light, the time dilation factor is about 7. This means that for every 1 year that passes on the ship, more than 7 years pass on Earth. This is not a science fiction fantasy. This is a proven fact of physics. That is why a journey that would take hundreds of years from Earth's perspective can fit into just a few decades for the passenger on the ship. The passenger can traverse enormous distances by aging less, biologically. But this is not a cheat to get around physics. This is a trade-off with the universe. The passenger gains distance, but pays a temporal price in return: temporal detachment. Because this journey is not just a journey through space, it is also a journey through history. An astronaut who leaves Earth and travels at a speed very close to the speed of light may not find the world they left behind when they return. This is the famous thought experiment known as the twin paradox. The twin who travels at high speed returns younger than the twin who stayed on Earth. This is not a paradox, because the passenger who accelerated and changed direction followed a different space-time path. But the emotional consequence of this is greater than the physics. The traveller is detached not just from their family, but from their era, their language, their culture, and perhaps even the social meaning of their mission. They are no longer an explorer, but a migrant from through time. During their journey to a star hundreds of light years away, centuries, or even millennia may pass on Earth. A message sent from home may arrive at the ship when the senders died generations ago. A report they send back may reach people who only know them as a name in the archives. Relativity allows a person to go very far within a biological lifetime, yes. But the price is sacrificing the time of everyone left behind. This is why the ultimate answer to how far we can go in a lifetime is not a single number, but a series of nested limits. First, the current technology limit. With the technology we have proven, we can go to the moon, and with great difficulty, attempt Mars. Second, the revolutionary technology limit. With engines reaching 10 to 50% of the speed of light, the nearest stars become a lifetime journey. But even this only applies to the closest neighbours a few light years away. The third is the relativistic limit. At speeds very close to the speed of light, a passenger can travel hundreds, even thousands of light years by their own clock. But this requires detaching from Earth's time and landing in a completely different future upon return. And this is perhaps the answer to why the universe is so quiet. Perhaps interstellar travel is equally difficult for every civilization. Perhaps the galaxy is not filled with easily traveling empires, but with islands of intelligence, slowly learning under their own sky. When we bring these concepts together, an incredible picture emerges before us. Scale, energy, biology, and time, all massive forces at war with each other. But in the midst of this war stands the most ingenious solution humanity has found for survival, creating an artificial world. Because on a long journey, a spaceship is no longer just a vehicle. So how exactly does this closed ecosystem, this mini-Earth that will keep a person alive for decades, actually work? And now, the real discoveries begin, because when we move beyond theoretical calculations, we are confronted with the brutal truths taught to us by human spaceflight. This is not an equation. This is lived experience, and every finding proves that the road to the stars is far more complex and dangerous than we thought. Here are the real findings. The first discovery was seemingly the simplest: orbit. When humanity first escaped Earth's gravity, it thought it had won a victory. But, in reality, it had just entered a state of continuous freefall. Low Earth orbit is only a few hundred miles above the surface. If the Earth were a classroom globe, the space station would be hovering just above the paint. But, even to reach this thin shell, a spacecraft must travel sideways at about 17,500 miles per hour. This speed ensures that while constantly falling around the Earth, it never hits the surface. But this situation was the beginning of a disaster for the human body, because in a zero-gravity environment, bones lose mineral density, muscles atrophy, fluids rush to the head, and blood vessels reshape themselves. This was the body adapting to space, but it was also slowly abandoning everything that kept it healthy on a planet. This finding was shocking, because we realized that the longer we stayed in space, the more alien we became to Earth. Orbit was not a destination, it was a port where a biological time bomb began to tick. But that was just the beginning. The real shock came when we left the port and embarked on our first true journey, the Moon, approximately 238,900 miles away. It sounds like a huge number. But, on an astronomical scale, it's close enough to touch. Just 1.3 light seconds, the Apollo missions crossed this distance and delivered one of humanity's greatest moments. But they also showed what a thin line we were walking. Tiny crews, very short stays, limited supplies, and most importantly, no long-term shelter. The Moon itself was not friendly. It has no air to breathe, no oceans, no global magnetic shield. It has only 1/6 of Earth's gravity. This is a level whose long-term effects on human physiology are still uncertain. The Moon taught us this: there is a huge difference between visiting space and living there. And the human body was the first thing to pay the price for that difference, because the Moon lacked all the protective layers that Earth provides. Radiation, micrometeoroids, and extreme temperature swings were a constant threat. The Moon journeys were a triumph, but they were also a warning. The farther we strayed from home, the harder it became to carry the conditions of home with us. Then we set our sights on Mars, and that's when the meaning of the word far completely changed. Mars is not a few days away. It is a moving planet on its own orbit, sometimes tens of millions of miles away, sometimes much more. The journey has to respect the dance of the two planets around the Sun. This means launch windows that open every 26 months, transfer times lasting for months, and long stays on the surface waiting for the planets to align again. Going to Mars was actually solving a celestial mechanics puzzle. But the biological findings were even more alarming. Mars's atmosphere is less than 1% of Earth's sea level pressure and is mostly carbon dioxide. Its average temperatures are brutally cold. It has no global magnetic field. This meant that the radiation exposure, both during the journey and on the surface, was one of the most fundamental biomedical concerns. If humans go to Mars with current chemical propulsion systems, the journey is possible in principle. But this is an unproven claim, because a rover can fail silently, but a crew cannot. Mars was where our current technology pushed its philosophical limits. It showed us this: reaching a planet is one thing, surviving on that planet and returning in good health is something else entirely. These three discoveries, orbit, the Moon, and Mars, taught us one bitter truth: the human body was not designed for the vacuum of space. At every step, we encountered a challenge for which our evolution had not prepared us. And as we looked farther out, to Jupiter, to Saturn, and beyond, we saw these problems grow exponentially. These planets could no longer be described by the word mission. They meant a lifetime sealed inside machines. So, in the face of these overwhelming biological and physical obstacles, does humanity still have any hope? Or will the stars remain behind a wall that our biology can never overcome? But there is a reason humanity does not give up. Because despite these overwhelming biological limits, engineering and physics are opening incredible doors, even if only in theory. And the discoveries behind these doors have the potential to redraw the boundaries of a human lifetime. This is why the real revolution is not in the engines, but in the fundamental understanding of physics behind the engines. The first major discovery was the evolution of propulsion systems. Chemical rockets are magnificent machines that launch the space age. But they are limited by the energy of chemical bonds. This is great for leaving Earth and traveling through the solar system with clever orbits. But it is completely inadequate for accelerating a human habitat to a significant fraction of the speed of light. This is where nuclear thermal propulsion comes in. This system uses a reactor to heat a propellant to temperatures far beyond chemical combustion. This could shorten travel times to Mars and improve deep space access. But even this is not enough to reach the stars in a lifetime, because the real revolution came with ion engines and electric propulsion systems, which use fuel more efficiently. These systems apply a gentle thrust for months by accelerating ions to high exhaust velocities. This constant whisper can turn into a massive change in velocity over time. This is an almost meditative technology for robotic probes. But for mission durations compatible with biology and human psychology, this whisper needs to be much stronger. That's why scientists are looking at much more radical concepts, like fusion. If it can be controlled in a compact and reliable form, fusion energy could create not just improved rockets, but new kinds of moving worlds. These discoveries showed us going faster didn't just mean burning more fuel, it meant changing the fundamental ways of releasing energy. But the most shocking discovery wasn't about propulsion. It was about the geometry of space travel, because spaceships don't travel in straight lines like in children's drawings. They move along gravitational fields, and you can use these fields to your advantage. This is called a gravity assist. By passing by a planet, you can steal a piece of its orbital energy. This reshapes the probe's path and increases its speed relative to the Sun. The Voyager probes use this technique masterfully. But this is not a magic slingshot to the stars. This is a technique that works within the energy economy of the solar system, and the gains, while extraordinary for exploration, are tiny next to the speeds needed to reduce light years to decades. The Parker Solar Probe can reach breathtaking speeds by diving deep into the Sun's gravity well. But that speed belongs to a specific orbit and thermal environment, not a starship gliding safely towards Alpha Centauri. This discovery taught us how misleading the word speed can be in space when taken out of context. A probe's fastest moment, its instantaneous velocity as it passes a planet, does not define the continuous cruising speed needed for a manned interstellar journey. Speed is much more than a number. It is the entire geometry of the mission. And then, we hit the darkest and most concrete wall in front of all these dreams of speed, the danger of high-speed collision, because as you accelerate, space itself becomes more dangerous. At a speed like 10% of the speed of light, an ordinary dust grain is no longer just a dust grain. It is a projectile carrying immense kinetic energy. The space between stars is not as empty as we think. It is thin, silent, and deadly when you pass through it very fast. Gas atoms become a high-speed particle stream. That's why the front of a relativistic starship must be unlike anything ever flown before. It might require layered shields, magnetic deflection, sacrificial materials, or active detection systems that turn the ship from a vessel into a moving fortress. But the most brutal part of this discovery is the half that is often forgotten. Stopping. A ship that arrives at a star system at 10% of the speed of light and cannot slow down, merely leaves that system with a brief scientific flyby. This would be useful for a probe, but almost tragic for humans. Arriving is not just passing by a target, it is reducing speed, entering a usable orbit, and staying long enough to give the journey meaning. And slowing down requires as much energy as speeding up. This doubles the energy problem. This discovery taught us that a lifetime interstellar journey is not just about going, it's also about arriving. When these findings came together, the picture that emerged was both hopeful and terrifying. Propulsion systems, gravity maneuvers, and the dangers of high speed, all are massive engineering problems to be solved. But at the center of all these machines and equations, there is a single purpose: to keep the fragile biological cargo inside alive. So, what technical systems must these machines, these artificial worlds, have to keep a human alive on a journey lasting for decades? So, how exactly does this closed ecosystem, this mini-Earth, that will keep a human alive on a journey lasting for decades, actually work? Because turning a spaceship from a vehicle into a world is the greatest engineering and biological challenge we have ever faced. Now, let's get into the technicals and see that a starship is not just made of engines, but must also be a living, breathing, and self-healing organism. The first and most fundamental mechanism is atmosphere management. This is like the lungs of the ship. On Earth, we don't notice the atmosphere. It is everywhere, providing oxygen for every breath and diluting carbon dioxide. But in a sealed metal box, air is a substance that requires constant engineering. Humans consume oxygen and produce carbon dioxide. If carbon dioxide builds up, it first fogs the mind, then poisons the body. That's why the ship needs systems that constantly scrub carbon dioxide from the air. But that's just the beginning, because the consumed oxygen must also be replaced. On long-term missions, this cannot be done with tanks brought from Earth. That's why oxygen is produced through methods like the electrolysis of water. But air is not just oxygen and carbon dioxide. There are hundreds of trace gases that off-gas from plastics, electronics, human metabolism, and cleaning supplies. If these gases accumulate, they can become toxic. That's why the air must be constantly filtered, purified, and monitored. Even airflow is a critical design feature on a starship, because in zero gravity, a sleeping astronaut could remain in a pocket of their own exhaled carbon dioxide and suffocate. This is why a starship's atmosphere is not just a mechanical system, it is a miniature climate system, and this system must work flawlessly for decades. The second critical mechanism is the water cycle. This is the ship's circulatory system. It's blood. Water is life. but it is also heavy. So you cannot take all the water you need for a long journey with you. The solution is to close the loop. This means reclaiming every single drop of water on the ship, and this includes reclaiming water from places that might seem emotionally strange on Earth. The moisture from astronauts' breath, wash water, and even urine. Yes, urine. Advanced filtration and purification systems put the urine through chemical and physical processes, turning it back into potable, pure water. This is not a moment of dramatic desperation. This is the basic mathematics of survival. Because even a 90% closed system means a slow leak over years, which could cause the mission to fail. A starship must treat water like a sacred circulatory organ. It is never just stored, it is constantly recycled. These systems must remove every kind of contaminant, microbe, and mineral from the water, producing water that is cleaner than even the purest waters on Earth. Because in a closed system, even the smallest contamination can grow over time into a fatal problem. That is why the water recycling system is not just a plumbing job. It is one of the most fundamental biological engines that ensures the ship's survival. But air and water are only part of the equation. The third and perhaps most complex mechanism is food production and waste management. This is the ship's digestive system and metabolism. For short missions, packaged foods are sufficient, but on a journey lasting decades, stored food loses its vitamins, takes up mass, and becomes a heavy psychological burden. That's why a true starship must have agriculture, not as a luxury add-on, but as part of the infrastructure. Plants are not just food, they're biochemical partners. They convert carbon dioxide, release oxygen, recycle nutrients, and balance humidity. But most importantly, they offer a living rhythm that machines do not have. The opening of a leaf under artificial light, millions of miles from Earth, is proof that life still goes on. However, space agriculture is not a simple romance. Plants require controlled light spectrums, root moisture, nutrient delivery, and pollination strategies. Every tomato grown in space is also an electrical, thermal, water, and microbial equation, and where there is agriculture, there is also waste. On Earth, waste disappears into large systems. But on a spaceship, there is no outside. The outside is still inside the mission. That's why waste must change its identity. Human waste and food scraps are not garbage. They are valuable resources like water, carbon, nitrogen, and phosphorus. The dream of a closed ecological life support system is actually the dream of turning a spaceship into a controlled metabolism. This system is a structure where chemistry, biology, and engineering switch roles, a structure that is neither purely natural nor purely mechanical. These three essential systems, air, water, and food, form the survival triangle of a starship. But all of these systems are based on one fundamental truth: they can break, and when help is millions of miles or light years away, the ship must be able to repair itself. So, when a failure occurs, how does this miniature world keep itself alive? What are the other critical mechanisms? Therefore, a starship must be not only a living ecosystem, but also a self-healing machine. The ship's nervous system and immune system come into play. This is the autonomous repair and diagnostic mechanism. On Earth, when a machine breaks, you call a repairman. But in deep space, the ship must be its own repairman, its own workshop, and its own spare parts depot. Pumps fail, valves jam, electronics break down. These are not possibilities, they are certainties. That's why the ship must be equipped with thousands of sensors that can detect failures before human intervention is needed. Just as the human body feels an infection, the ship must feel an abnormal vibration in a pump or a voltage drop in an electronic board. This is done with AI-powered diagnostic systems. These systems maintain a health map of the ship's normal operating parameters and analyze even the smallest deviations. But diagnosis is not enough. Repair is also needed. That's why modular design becomes critical. A failing part should be a module that can be easily replaced. Spare parts are stored on the ship. But what if you need a part you don't have? That's when additive manufacturing, or 3D printers, come into play. The ship must be able to produce the tools or parts it needs itself. This turns the ship from just a vehicle into a self-sustaining industrial facility. This reduces the mass of spare parts and provides flexibility against unforeseen problems. This mechanism requires the crew to be not just passengers, but also engineers, doctors, repairmen, and systems thinkers. Because the ship's survival depends on the fusion of these autonomous systems and the crew's intelligence. But all these mechanical and ecological systems ignore perhaps the most unsolved and fundamental technical problem: gravity. This is the ship's skeletal structure. The human body evolved to resist the constant downward pull of a planet. When you remove that pull, the body begins to break itself down. Bones lose density, muscles weaken, the cardiovascular system grows lazy. Exercise can mitigate these effects, but it may not be enough for a journey lasting decades. That's why, for a long-term mission, the most serious technical solution is artificial gravity, and the most realistic way to create it is rotation. Just as the water in a bucket doesn't spill when you swing it around your head, a rotating habitat can create a sensation of gravity through centrifugal force. The floor is constantly pushing up towards you. But this solution requires massive engineering trade-offs. For a comfortable rotation speed, one that doesn't cause motion sickness, the diameter of the habitat needs to be quite large. A small room would have to spin too fast, which is disorienting for the inner ear. A large structure, however, means enormous mass, balance issues, and structural stress. This brings us back to that ruthless equation where mass requires thrust, and thrust requires energy. A starship might consist of two massive rings fighting each other, or rotating modules extending from a central hub by tethers. But this means that bearings, rotating seals, and docking mechanics must work flawlessly for decades. Artificial gravity may not be a luxury, but a biological necessity, and this necessity fundamentally shapes the ship's design. It is no longer a simple cylinder, but a complex, rotating world trying to imitate a planet for its inhabitants. And this world must have a shield against the greatest external threat. This is the radiation shielding mechanism, the ship's skin and atmosphere. Earth's magnetic field and atmosphere protect us from most of the dangerous particles from the Sun and the galaxy. But in deep space, this protection is gone. The ship must create its own shield. There are two main types of threats: solar particle events and galactic cosmic rays. Solar storms are sudden and intense bursts of energy. Against these, a storm shelter can be built inside the ship. This is a more densely protected area, surrounded by water tanks, food stores, or hydrogen-rich materials. But galactic cosmic rays are more insidious and difficult. They are a constant bombardment, and very high-energy particles can actually make the situation worse by creating secondary radiation when they hit simple shields. That's why passive shielding is one of the most effective methods. This means burying the crew's living quarters behind thick layers of hydrogen-rich materials like water, fuel, or polyethylene. Hydrogen is effective at slowing down these particles. But this significantly increases the ship's mass. In the future, active shielding might also be an option. This is the idea of creating a magnetic or electrostatic field around the ship to deflect incoming charged particles, just like Earth's magnetosphere. However, this is a massive engineering problem that has not yet been solved, because creating a field that is strong and reliable enough would require enormous amounts of energy and could introduce its own new dangers. The radiation shield is one of the heaviest and most passive but also one of the most vital systems of the ship. It is a copy made of metal and water of the sky and magnetic field that Earth gives us for free: repair, gravity, and radiation. These three technical mechanisms, combined with the life support systems, show just how complex a structure a starship is. It must be an ecosystem, a machine, a planet, and a fortress, all at the same time, and at the heart of all these systems is perhaps the most delicate and powerful of all, the human mind. Because even the most perfect machine becomes meaningless if the people inside it mentally collapse. But what's truly exciting is how these technologies could make it possible not just to survive, but to transcend the limits of a human lifetime. So, what exactly are these engine technologies, these starship engines, that will allow us to reach these incredible speeds? And on what frontiers of physics do they operate? And now comes the real miracle. because all these survival systems and theoretical engines are only preparing us for the next step, the climax, the incredible speeds that push the limits of a human lifetime, that are hidden in the deepest layers of physics, and that turn a journey from a mere trip into a leap in time itself. Now the tempo increases, because we are no longer talking about survival, but about redrawing the map of the universe. Here are the epic moments when a human lifetime can reach for the stars. The first epic moment is 1% of the speed of light. It sounds small. Just 1%. But, in the language of engineering, it is a revolution. This means about 3,000 kilometers per second, or more than 10 million kilometers per hour. This speed is hundreds of times faster than the Apollo capsules. The fastest manned vehicle we have ever built. This is a speed unseen in history. At this speed, you would cover the 384,000 kilometer distance from Earth to the Moon, not in days, but in just over 2 minutes. This is a record time in human history. Mars, at its closest approach, would become a neighbor reachable in just hours, instead of a journey lasting for months. You would pass Jupiter's orbit in a few days, and Neptune's orbit in less than 3 weeks. This is a speed that finally brings the vast architecture of the solar system down to the scale of human planning. For the first time, a human lifetime could be long enough to visit all the planets. But how could this speed be possible? Because this completely surpasses the limits of chemical rockets. This requires propulsion systems with much higher energy density, like nuclear fusion or antimatter, that convert mass directly into energy. The scientific community understood that this speed was not just an engineering challenge, it was a paradigm shift in how we control energy. This speed would make us masters of the solar system. But, for the stars, it was still insufficient, because even at this record speed, reaching Proxima Centauri would take exactly 425 years. This was not a lifetime, it was a dynasty. That is why this moment was both an epic victory and a bitter lesson. Conquering the solar system was only the first step to reaching the stars. But there was something bigger, much bigger. The second epic moment is 10% of the speed of light, 0.1 c. This is the threshold that changes everything. This is the first moment that the stars mathematically enter a human lifetime. This speed is 30,000 kilometers per second. This is 1/10 the speed of light itself. This is dangerously approaching the universal speed limit. At this speed, you cover 1 light year in 10 years. What does this mean? The journey to Proxima Centauri, 4.25 light years away, would be reduced to about 42 or 43 years with an ideal cruise calculation. For the first time in history, the nearest star ceases to be a myth and becomes a lifetime's dedication. An astronaut who sets off in their 20s, after spending their entire adult life in the interstellar darkness, could reach their destination in old age. Barnard's star, about 6 light years away, would be a journey of about 60 years at this speed. Sirius, a little over 8 light years away, would take more than 80 years. This is a duration that pushes the limits of a normal human lifespan. But how could it be possible? This speed requires not just engines like fusion, but perhaps radical concepts like beamed energy, using massive laser arrays to push the ship. This means leaving the power source at home, instead of carrying it on the ship. But the scientific community experienced the real shock in the energy requirements, because the kinetic energy needed to reach this speed is on a civilizational scale. This is not the budget of a single mission, but the collective decision of an entire planet. At this speed, even the smallest dust grain turns into a bomb. That's why the ship's front shield becomes one of its most important structures, and the problem of slowing down doubles the energy equation. 10% of the speed of light gave us the first true Starship lifetime. But it came with a warning written into every equation. Reaching the speed is only half of reaching the star. And then, the most incredible thing happened, a moment that pushes the limits of imagination. The third epic moment, 50% of the speed of light, 0.5 c. This is no longer just engineering, it is dancing with physics itself. At this speed, the map of the universe is reshaped. Proxima Centauri becomes a journey of only 8.5 years by Earth's calendar. Stars 20 light-years away become achievable targets with a 40-year journey. The local bubble around the Sun begins to look not like an unreachable ceiling, but like a dark ocean filled with islands. At this speed, a traveller could cover distances that would make 0.1 c feel patient and 0.01 c feel ancient. But this speed also visibly plunges us into a relativistic world. Time dilation is no longer a theoretical detail. It is a lived reality. The Lorentz factor is about 1.15. This means a journey measured as 8.5 years on Earth would feel slightly shorter for those on the ship. But how is this speed possible? This might require energy sources at the very edge of known physics, like antimatter propulsion. Because the kinetic energy of this ship is no longer just large, it is frightening. This ship is no longer just fast. It is an object carrying concentrated motion, and a collision with even the smallest object could result in catastrophe. The interstellar medium turns into a high-speed particle stream coming from the front of the ship. The ship needs layered sacrificial shields, active detection systems, and perhaps plasma-based deflection systems. Even light itself changes character. The stars in front blue shift, the ones behind red shift. The sky is no longer the calm sphere we see from Earth. It is a landscape directionally transformed by motion. The scientific community understood that this speed was not just a propulsion problem. It was an architecture of survival. And a civilization that traveled at this speed had to control energy at a godlike level. But all these speeds pale in comparison to the universe's final and greatest gift. The fourth epic moment is to conquer time itself, because as you approach the speed of light, the strangest and most powerful effect comes into play: time dilation. This is not just an acceleration, it is a journey through time. At 99% of the speed of light, the Lorentz factor exceeds 7. For every 1 year that passes on the ship, 7 years pass on Earth. At 99.9% of the speed of light, this factor jumps to about 22. At 99.999%, it exceeds 223. What does this mean? It means a journey that takes centuries on Earth could fit into just a few years for the passenger on the ship. It means it is theoretically possible for a human use within their biological lifetime to go not just to the nearest stars, but to the center of the galaxy and even beyond. For the first time in history, a human lifetime could extend to a galactic scale. How could this be possible? This would require a scenario where the ship constantly accelerates at 1g, providing the crew with Earth-like gravity and reaching incredible speeds over time. But this means an unimaginable amount of energy and propellant. The kinetic energy of this ship would be so great that anything it hit would release energy equivalent to a nuclear explosion. Even the sparse interstellar gas in front of it would turn into a deadly stream of radiation. This is the ultimate journey that physics allows. But it also demands the greatest price. The passenger travels not only in space, but also in time. When they return, only history books might remain of the civilization they left behind. This is the moment humanity flirts with immortality, but also the moment it is forever severed from its own history. These 4 epic moments show just how flexible the limits of a human lifetime can be. From the conquest of the solar system, to the journey to the nearest stars, to the exploration of the local stellar neighborhood, to a journey through time in the galaxy itself, each step requires more energy, more danger, and a greater sacrifice. But they all point to one fundamental question. At the end of all these incredible journeys, what will we find when we return home? And what does this mean for humanity? Therefore, what this means for humanity is far more profound than we can imagine. Because these journeys push not only the boundaries of physical distance, but also the boundaries of our identity. Each new speed threshold redefines what it means to be human. We are no longer bound to just one planet. We potentially belong to the stars, and the epic moments that unlock this potential are a testament not only to our engines, but also to our imagination and our sacrifice. Now, let's pull back the final and most dramatic curtains on the dance between a human lifetime and the universe. And now comes the greatest price. The 5th epic moment. isolation. This is not a speed, it is a state. But it is perhaps the heaviest burden of the entire journey, because as the distance increases, the connection with Earth is severed. This is a slow and ruthless process. On Mars, the communication delay can exceed 20 minutes. This turns every conversation into an exchange of letters. In an emergency, an answer from Earth arrives 40 minutes later. This is the first time in history that a part of humanity is completely cut off from instantaneous help. But this is only the beginning. At Jupiter, this delay is tens of minutes. At Saturn, it is over an hour. And in interstellar space, the delay turns into years. A crew on Proxima Centauri, 4.25 light-years away, when they send a message to Earth, must wait at least 8.5 years for a reply. This is a loneliness unprecedented in history. This means the crew must be completely independent, not just technically, but also politically, medically, and emotionally. The ship must carry not only the tools, but also the authority, not just the data, but the judgment. Not just the instructions, but the culture. How can this be possible? This means that crew selection becomes the most important decision in human history, because narrow corridors, constant noise, artificial light, and unresolved tensions can become more dangerous over the years than a faulty pump. A long-duration ship needs not just discipline, but a livable culture. It needs ways for grief, boredom, fear, and purpose to move through the crew without poisoning the closed emotional atmosphere. The scientific community has realized that these soft problems are actually the hardest engineering problems, because the most perfect ship, if the society inside it collapses, is nothing more than a coffin drifting through space. But what if there is a way to overcome this isolation? Here is the sixth and most speculative epic moment: suspended animation, hibernation. This is a solution dreamed of to reduce life support demands and alleviate the psychological burden of the journey. This is the most radical way to push the limits of a human lifetime. It sounds like science fiction, but it is based on real scientific research. The idea is to slow down human metabolism, inducing a state of torpor, just as some animals hibernate. This could significantly reduce the consumption of food, water, and oxygen. A journey that would take several decades could feel like only a few months of sleep for the crew. This could also reduce the duration of radiation exposure. This means that for the first time in history, we have the potential to manipulate biological time itself. This is not speeding up, this is pausing time. But how is this possible? This requires medical research to solve the deepest secrets of human physiology. Safely lowering body temperature, slowing metabolism, and restarting it decades later without cellular damage. This is a massive problem that has not yet been solved, and it brings with it moral questions. The scientific community stresses that long-term human suspended animation is still speculative. It is a possibility being investigated, not a solved answer. But if it becomes possible one day, it would completely change the equation of interstellar travel. The problem would no longer be how much can we fit into one lifetime. The problem would become how long can we extend one lifetime, and now the final, greatest moment, the destination of all these journeys. The seventh epic moment, a new world. This is the greatest leap in human history. Not just setting foot on another planet, but finding a habitable world in the orbit of another star and settling there. This means crossing a 4 billion-year-old boundary. Life born on Earth, taking root under the light of another sun. This is the moment humanity becomes not just a species, but a galactic species. How can this be possible? This requires not only the ship to slow down, but also to adapt to the conditions of the new planet. Creating an atmosphere there, finding water, farming, and protecting against radiation. This is a planet-scale engineering project known as terraforming. But it may also require biological adaptation. Perhaps over generations, a new type of human emerges, adapted to the conditions of the new world. The scientific community knows that this is not just a technological dream, but also brings with it deep philosophical and ethical questions. Do we have the right to change another world? And how does that world change us? This is the moment the future of humanity will be written. The moment we are no longer just children of Earth, but also children of the stars. This is the ultimate reward of a lifetime's journey, a second home, isolation, hibernation, and a new world. These epic moments are the ones that push the limits of a lifetime, that make us question everything that makes us who we are, and that reshape the destiny of humanity. Speed, energy, biology, time, and society. They all converge into one big question. At the end of all these incredible journeys, all these sacrifices, and all these triumphs, who are we? But now it is time to stop and think. After this dizzying speed and these epic moments, we must pull back and look at the big picture. So what do these journeys mean for us as a species, as a civilization? But now it is time to stop and think. After these dizzying speeds, these epic moments, and these incredible technological dreams, we must pull back and look at the big picture. Because these journeys make us question not only where we can go, but also who we are. Behind all these equations, all these rockets, and all these distances stands the most fundamental and most unsettling question. What is our place in the universe? Now, we descend into the deepest and most philosophical layers of this question, detection systems, and perhaps plasma-based deflection systems. Even light itself changes character. The stars in front blue shift, the ones behind red shift. The sky is no longer the calm sphere we see from Earth. It is a landscape directionally transformed by motion. The scientific community understood that this speed was not just a propulsion problem. It was an architecture of survival. And a civilization that traveled at this speed had to control energy at a godlike level. But all these speeds pale in comparison to the universe's final and greatest gift. The fourth epic moment is to conquer time itself. Because as you approach the speed of light, the strangest and most powerful effect comes into play. Time dilation. This is not just an acceleration, it is a journey through time. At 99% of the speed of light, the Lorentz factor exceeds 7. For every 1 year that passes on the ship, 7 years pass on Earth. At 99.9% of the speed of light, this factor jumps to about 22. At 99.999%, it exceeds 223. What does this mean? It means a journey that takes centuries on Earth could fit into just a few years for the passenger on the ship. It means it is theoretically possible for a human use within their biological lifetime to go not just to the nearest stars, but to the center of the galaxy and even beyond. For the first time in history, a human lifetime could extend to a galactic scale. How could this be possible? This would require a scenario where the ship constantly accelerates at 1g, providing the crew with Earth-like gravity and reaching incredible speeds over time. But this means an unimaginable amount of energy and propellant. The kinetic energy of this ship would be so great that anything it hit would release energy equivalent to a nuclear explosion. Even the sparse interstellar gas in front of it would turn into a deadly stream of radiation. This is the ultimate journey that physics allows. But it also demands the greatest price. The passenger travels not only in space, but also in time. When they return, only history books might remain of the civilization they left behind. This is the moment humanity flirts with immortality, but also the moment it is forever severed from its own history. These 4 epic moments show just how flexible the limits of a human lifetime can be. From the conquest of the solar system, to the journey to the nearest stars, to the exploration of the local stellar neighborhood, to a journey through time in the galaxy itself, each step requires more energy, more danger, and a greater sacrifice. But they all point to one fundamental question. At the end of all these incredible journeys, what will we find when we return home? And what does this mean for humanity? Therefore, what this means for humanity is far more profound than we can imagine. Because these journeys push not only the boundaries of physical distance, but also the boundaries of our identity. Each new speed threshold redefines what it means to be human. We are no longer bound to just one planet. We potentially belong to the stars, and the epic moments that unlock this potential are a testament not only to our engines, but also to our imagination and our sacrifice. Now, let's pull back the final and most dramatic curtains on the dance between a human lifetime and the universe. And now, comes the greatest price. The fifth epic moment: isolation. This is not a speed, it is a state. But it is perhaps the heaviest burden of the entire journey, because as the distance increases, the connection with Earth is severed. This is a slow and ruthless process. On Mars, the communication delay can exceed 20 minutes. This turns every conversation into an exchange of letters. In an emergency, an answer from Earth arrives 40 minutes later. This is the first time in history that a part of humanity is completely cut off from instantaneous help. But this is only the beginning. At Jupiter, this delay is tens of minutes. At Saturn, it is over an hour. And in interstellar space, the delay turns into years. A crew on Proxima Centauri, 4.25 light-years away, when they send a message to Earth, must wait at least 8.5 years for a reply. This is a loneliness unprecedented in history. This means the crew must be completely independent, not just technically, but also politically, medically, and emotionally. The ship must carry not only the tools, but also the authority, not just the data, but the judgment. Not just the instructions, but the culture. How can this be possible? This means that crew selection becomes the most important decision in human history, because narrow corridors, constant noise, artificial light, and unresolved tensions can become more dangerous over the years than a faulty pump. A long-duration ship needs not just discipline, but a livable culture. It needs ways for grief, boredom, fear, and purpose to move through the crew without poisoning the closed emotional atmosphere. The scientific community has realized that these soft problems are actually the hardest engineering problems, because the most perfect ship, if the society inside it collapses, is nothing more than a coffin drifting through space. But what if there is a way to overcome this isolation? Here is the sixth and most speculative epic moment: suspended animation, hibernation. This is a solution dreamed of to reduce life support demands and alleviate the psychological burden of the journey. This is the most radical way to push the limits of a human lifetime. It sounds like science fiction, but it is based on real scientific research. The idea is to slow down human metabolism, inducing a state of torpor, just as some animals hibernate. This could significantly reduce the consumption of food, water, and oxygen. A journey that would take several decades could feel like only a few months of sleep for the crew. This could also reduce the duration of radiation exposure. This means that for the first time in history, we have the potential to manipulate biological time itself. This is not speeding up, this is pausing time. But how is this possible? This requires medical research to solve the deepest secrets of human physiology. Safely lowering body temperature, slowing metabolism, and restarting it decades later without cellular damage. This is a massive problem that has not yet been solved, and it brings with it moral questions. The scientific community stresses that long-term human suspended animation is still speculative. It is a possibility being investigated, not a solved answer. But if it becomes possible one day, it would completely change the equation of interstellar travel. The problem would no longer be how much can we fit into one lifetime. The problem would become how long can we extend one lifetime, and now the final, greatest moment, the destination of all these journeys. The seventh epic moment, a new world. This is the greatest leap in human history. Not just setting foot on another planet, but finding a habitable world in the orbit of another star and settling there. This means crossing a 4 billion-year-old boundary, life born on Earth, taking root under the light of another sun. This is the moment humanity becomes not just a species, but a galactic species. How can this be possible? This requires not only the ship to slow down, but also to adapt to the conditions of the new planet. Creating an atmosphere there, finding water, farming, and protecting against radiation. This is a planet-scale engineering project known as terraforming. But it may also require biological adaptation. Perhaps over generations, a new type of human emerges, adapted to the conditions of the new world. The scientific community knows that this is not just a technological dream, but also brings with it deep philosophical and ethical questions. Do we have the right to change another world? And how does that world change us? This is the moment the future of humanity will be written. The moment we are no longer just children of Earth, but also children of the stars. This is the ultimate reward of a lifetime's journey, a second home, isolation, hibernation, and a new world. These epic moments are the ones that push the limits of a lifetime, that make us question everything that makes us who we are, and that reshape the destiny of humanity. Speed, energy, biology, time, and society. They all converge into one big question. At the end of all these incredible journeys, all these sacrifices, and all these triumphs, who are we? But now it is time to stop and think. After this dizzying speed and these epic moments, we must pull back and look at the big picture. So what do these journeys mean for us as a species, as a civilization? But now it is time to stop and think. After these dizzying speeds, these epic moments, and these incredible technological dreams, we must pull back and look at the big picture. Because these journeys make us question not only where we can go, but also who we are. Behind all these equations, all these rockets, and all these distances stands the most fundamental and most unsettling question. What is our place in the universe? Now, we descend into the deepest and most philosophical layers of this question. The first and greatest contrast is the contrast of scale. On one hand, there is the incredible fragility of the human body, a biology meticulously tuned by evolution for the surface of a planet, a life dependent on a single atmospheric pressure, a single gravity, a single magnetic shield. On the other hand, there is the mind-boggling vastness of the universe this body tries to understand. The 4.25 light-year distance to Proxima Centauri is about 40 trillion kilometers. It is impossible to visualize this number in our minds. How can such a small and dependent being comprehend such a vast stage and even dream of traveling on it? The tragic side of this question is our physical limitations. Our bodies cannot withstand the brutal conditions of interstellar space. Our bones dissolve, our muscles weaken, radiation tears our cells apart. We are beings who must carry our own small and fragile aquarium, the spaceship, with us to survive in the ocean of this universe. This is our cosmic tragedy. The universe was not made for us, and we were not made for the universe. But within this tragedy lies an incredible beauty, because no matter how small and limited we are physically, our minds are limitless. Newton, by showing that a falling apple and the orbit of the planets obey the same mathematical order, transformed the heavens from a divine ceiling into a calculable system. Einstein showed that space and time are not a fixed background, but a unified fabric shaped by motion itself. We do not just observe this vast universe, we understand its rules, and this act of understanding is the greatest leap that transcends our physical limits. You are a part of this contrast. You, us too, carry within this fragile body that incredible mind capable of contemplating trillions of kilometers and billions of years. The greatest paradox of our existence is this. We are physically a speck of dust, but in our capacity to understand, we are as vast as the universe itself. The second contrast is the contrast of time. On one hand, there is the human lifespan of about 80 years. This period feels very long to us. We fit into it childhood, love, grief, work, the seasons, and the accumulation of memories. On the other hand, there are the units of measure of the universe. It takes more than 4 years for light to reach the nearest star. It takes more than 100,000 years for light to cross our galaxy from end to end. The age of the universe is about 13.8 billion years. How can such a fleeting moment find meaning in such an infinite timeline? The tragic side of this question is our transience. A human life, seen from Earth, is like a candle flame. The galaxy is an ocean where even light passes like a patient tide. Our entire history, our entire civilization, is less than a blink of an eye on this cosmic calendar. The stars shone for billions of years before we were born, and they will continue to shine for billions of years after we're gone. This is humanity's deepest sorrow in the face of the universe. We are only a moment, and that moment will pass. But within this transient lies a breathtaking beauty, because that brief moment is the only moment the universe can witness itself. The light of the stars passes through lifeless atoms and empty space that have existed for billions of years. But only when that light reaches the eyes of conscious beings like us does it become beauty. Only in our minds do those orbits become elegance. Only in our hearts does that distance become longing. The universe knows itself through us. We are the way the universe becomes self-aware, and this is the greatest meaning that can be squeezed into a short lifetime. You are a part of this moment. You too right now are a carrier of that miraculous consciousness through which a universe of billions of years can think about itself. Your existence in this infinite ocean of time is the briefest but most precious poem the universe has written to itself. And the third contrast is the contrast of loneliness. On one hand, there is humanity's deep loneliness in space. The Voyager probes, after being launched in 1977, have been travelling for nearly half a century. But they have still only reached a distance on the scale of light hours, not light years. They are humanity's farthest ambassadors, but also its loneliest parts. The farther a spaceship goes, the more isolated it becomes. This is not just a measurement, it is a feeling. On the other hand, even in this loneliness, there is humanity's incredible connection to each other. A starship is not the work of a single hero. It is the result of the collaborative effort of tens of thousands of scientists, engineers, technicians, and dreamers. It is a carrier made of metal and software, a source of knowledge, culture, and hope accumulated over generations. How can it be that the individual who goes farthest is also connected to the greatest number of people? The tragic side of this question is the separation that distance brings. An interstellar traveller cannot have a real-time connection with their loved ones on Earth. Their voices are echoes from the past. The longer the journey, the weaker this bond becomes. The traveller eventually becomes an island, not just geographically, but also emotionally and culturally. This is the greatest price of humanity's greatest explorations, having to leave behind in order to move forward. But within this separation lies one of the most powerful beauties, because every system inside that spaceship is a testament to the intelligence and labour of a team on Earth. The air recycling system is a monument to the engineers who purify water. The radiation shield is a symbol of the protective arms of physicists. Every tomato the crew eats is a victory for the botanists who managed to grow that plant in space. That ship, E, is not alone. It is filled with the best parts of humanity, its intelligence, its cooperation, and its love. It is a vessel of humanity's collective spirit. You are a part of this connection. You, too, on this planet, are a member of the civilization that ensures the survival of those distant travellers. Your existence is proof that even the loneliest person is actually never alone. These contrasts of scale, time, and loneliness define our place in the universe. Small but understanding, transient but meaningful, alone but connected. This is our story. But there are more layers to discover on this philosophical journey. So how do these journeys shape our future as a species? And these journeys inevitably shape our future as a species, because the dream of reaching for the stars is not just a technological goal, but also a mirror that tests the character of our civilization. This mirror shows us our deepest fears and our greatest hopes, and in this process, perhaps the most important discovery will not be the universe itself, but what we learn about ourselves while confronting it. The fourth and most unsettling contrast is the contrast of knowledge and ignorance. On one hand, we know more than at any other moment in human history. Newton taught us the language of gravity. Einstein showed us that space and time are flexible. Rocket engineers turned these equations into machines that allowed us to escape Earth. We can calculate the orbits of planets with Kepler's ellipses with precision. We know the speed of light to be about 300,000 kilometers per second. This is an incredible mastery over the workings of the universe that surrounds us. On the other hand, there is a vast ocean of ignorance illuminated by this knowledge. Because every answer we learn gives birth to 10 new questions. We know that interstellar space is filled with radiation, but we do not fully know the decades-long effects of this radiation on the human brain. We know that a spaceship must be a closed ecosystem, but we cannot predict how the microbial balance of this ecosystem will change over years and affect the crew's health. We know that relativistic speeds bend time, but we can only imagine the psychological impact of this. What it means for a person to be cut off from their own history. How can it be that as our knowledge increases, our awareness of what we do not know also increases so much? The tragic side of this question is that the journey itself is the greatest unknown. We can make the best plans, build the most robust ships. But, in interstellar space, the possibility of facing an unforeseen problem we have never encountered before is always there. This is the deep humility that even the bravest explorers feel. The universe will always be bigger and more surprising than us. But, within this ignorance lies the greatest beauty, because not knowing is the fuel for the desire to learn. The unknown is the heart of discovery. If we knew everything, we would have no reason to set out. What draws us to the stars is not just the hope of finding out what is there, but also not knowing what we will learn about ourselves along the way. Space travel is not just about going to a destination, it is a learning process. And in this process, failures are at least as valuable as successes. You're a part of this contrast. You too every day live between the security of what you know and the curiosity of what you don't. Your personal journey, just like humanity's journey to the stars, is a step from the small island illuminated by knowledge into the infinite ocean of ignorance, and the final contrast, the most human one, the contrast of dream and reality. On one hand, there is the bright, clean, and easy interstellar travel dream presented to us by science fiction. Ships that accelerate instantly, friendly aliens, and Earth-like planets. These dreams are a reflection of our deepest hopes and desires. The desire not to be alone in the universe, to make a new start, and to transcend our limits. On the other hand, there is the brutal reality presented to us by physics and engineering, the unforgiving mathematics of the rocket equation, the invisible danger of radiation, the crushing loneliness brought by distance, and the almost impossible complexity of keeping a spaceship operational for decades. Reality is much harder, much slower, and much more dangerous than our dreams. How can the gap between these two pictures be so large? The tragic side of this question is the potential for our dreams to disappoint us. When we realize that reaching the stars is not a romantic adventure as we thought, but a tedious, dangerous, and sacrificial job, we face the risk of giving up. The cold face of reality can freeze even the warmest dreams. But within this gap lies our greatest strength, because dreams are like blueprints that shape reality. When Jules Verne dreamed of traveling to the moon, it was just a fantasy. But that fantasy inspired pioneers like Tsiolkovsky, Goddard, and von Braun. They turned that dream into equations, and then into rockets. Our dreams show us what is possible. Reality teaches us how to get there. One is meaningless without the other. Our dreams are the engine that pushes us forward. Reality is the rudder that keeps us on course, and the combination of these two is the formula for humanity's greatest achievements. You are a part of this contrast. You, too, every day, live in that space between the person you want to be and the person you are. Your dreams are your personal stars, and the challenges of reality are the ship you must build to reach those stars. The story of humanity is born from that creative tension between the two. These philosophical reflections, thoughts on scale, time, loneliness, knowledge, and imagination offer us a profound perspective on our place in the universe. We now know that our journey to the stars is not just an outward journey, but also a deep inner journey. It is a journey to discover who we are and who we can be. But, at the end of this journey, all these thoughts bring us to one big question. Despite all these difficulties, all these sacrifices, and all these uncertainties, why do we want to go? What lies at the root of this deep and irresistible urge? Therefore, now is the time to ask the most internal question, because despite all these difficulties and uncertainties, that irresistible urge is still there, the urge to go. This is one of the most fundamental drives of the human spirit, to wonder what lies beyond the horizon. But this curiosity is not just a search for an answer, It is a search for deeper meaning. And in this search, we confront the final and most personal contrasts that define our relationship with the universe. First, we face the contrast of power and powerlessness. On one hand, there is the incredible technological power we have achieved as a species. We have built rockets that can defeat our planet's gravity. We have sent humans to the moon. We have sent robotic envoys to every corner of the solar system. We know the theoretical ways to unleash the energy of fusion and antimatter. This is a demonstration of mastery over the forces of nature. This is a power once attributed only to gods. On the other hand, even in the midst of this power, there is our absolute powerlessness in the face of the fundamental laws of the universe. We cannot exceed the speed of the light. This is the universe's most basic traffic rule, and no technology can change it. We cannot escape the second law of thermodynamics. Every system inevitably moves towards disorder. And most importantly, we cannot escape the one-way flow of time. We can slow it down with relativistic journeys, but we can never reverse it. How can it be that while we imagine energies that could move planets on one hand, we are so tightly bound by the simplest and most fundamental rules on the other? The tragic side of this question is the moment our ambition collides with our limits. No matter how powerful we become, we do not set the rules of the universe. We are just learning to play within those rules. This is sometimes a feeling of disappointment, the feeling that our limitless potential is surrounded by invisible walls. But within this powerlessness lies our greatest wisdom, because understanding our limits is the beginning of our creativity. Because we cannot exceed the speed of light, we discovered relativity and time dilation. Because we cannot go everywhere with brute force, we learned elegant maneuvers like the gravity assist. Our limits force us to be smarter, more efficient, and more thoughtful. They are not a prison, but a teacher. And learning these lessons is the truest definition of our power. You are a part of this contrast. You, too, every day, walk that fine line between the things you can change and the things you must accept. Your personal power emerges not just in what you can do, but also when you understand what you cannot do, and that understanding is the greatest freedom. Second, we encounter the contrast of home and exile. On one hand, there is our deep and rooted connection to Earth. This is our only home, the planet that shaped us, the place where every cell of our bodies comes from its oceans, atmosphere, and soil. The word home is more than just a place. It is a feeling of security, of belonging, and of identity. On the other hand, there is our desire to leave this home, to seek new worlds, and to spread ourselves across the universe. This is a kind of self-imposed exile. To go to the stars is also to leave home, and the farther we go, the more impossible it becomes to return to that home. How can it be that while we are so deeply attached to our home on one hand, we feel such a great desire to leave it on the other? The tragic side of this question is that both choices involve a loss. If we stay on Earth, we miss out on the potential of the stars. If we go, we lose the familiarity and comfort of our home. On a relativistic journey, we go into exile not just geographically, but also temporally. When we return, home is no longer the home we left. This is the explorer's greatest loneliness. They have a new place to go, but no home to return to. But hidden within this exile is one of the deepest meanings, because leaving home is also learning to carry the concept of home with us. A starship is an Earth made of metal. The air, water, and plants inside are echoes of Earth. The crew's traditions, stories, and music are seeds of Earth's culture. By leaving home, we actually understand better what home means. We take it with us, not as a planet, but as an idea, as a set of values. And perhaps humanity's ultimate destiny is not to be tied to a single planet, but to plant home seeds across the universe. You are a part of this contrast. You, too, in your life, make choices between the security of the familiar and the call of the unknown. And with every new step you take, you expand the boundaries of your home a little more. Because home is not just where you were born, but every place where you find meaning. And finally, we face the contrast of silence and sound. On one hand, there is the great silence of the universe. The sky, though filled with stars, is quiet. The unsettling question of the Fermi paradox remains unanswered. Where is everybody? Despite billions of galaxies, trillions of stars, and countless planets, why do we see no evidence of other intelligent life? This silence seems to be the greatest proof of our cosmic loneliness. Perhaps we are truly alone. Perhaps in this vast universe, we are the only conscious beings. On the other hand, in the midst of this silence, there is an incredible sound created by humanity. Our science, our art, our music, our philosophy. Our equations that try to understand the laws of the universe. Our poems that question the meaning of our existence. Our messages to the universe, like Voyager's golden records, that tell who we are. We may be the only voice in this silent universe, creating meaning, asking questions, and seeking answers. How can it be that in such a great silence, such a meaningful sound can rise from such a small planet? The tragic side of this question is the possibility that this sound will not be heard. Perhaps the universe speaks in ways we cannot hear. Perhaps other civilizations have existed and disappeared long before we started listening. Perhaps our voice is nothing more than a faint whisper lost in this vast void. This is one of our deepest fears. We are speaking, but no one is listening. But within this silence lies our greatest responsibility and our greatest honor. If we are the only voice in this universe, then it is our duty to preserve, develop, and further amplify this voice. Then our science is not just a curiosity, but the universe's effort to understand itself. Then our art is not just an entertainment, but a trace of beauty left in this silence. Then our desire to go to the stars is not just an exploration, but the responsibility to carry this consciousness, this voice, to other corners of the universe. You are a part of this contrast. You, too, in the silent moments of your own life, create your own inner voice, your own meaning, your thoughts, your questions, and your dreams are notes added to this great cosmic choir. Power, home, and sound. These final contrasts show that our journey to the stars is not just a physical, but also a spiritual quest. It is a journey to discover our limits, our belonging, and our meaning. But, after all this philosophical depth, the most practical and ultimate question remains. So, when we put all this together, what is the final answer? Therefore, now is the time to ask the most internal question. Because despite all these difficulties and uncertainties, that irresistible urge is still there, the urge to go. This is one of the most fundamental drives of the human spirit, to wonder what lies beyond the horizon. But this curiosity is not just a search for an answer, it is a search for deeper meaning. And in this search, we confront the final and most personal contrasts that define our relationship with the universe. First, we must face the contrast of patience and urgency. On one hand, there is the urgency of human civilization. Life is short, our problems are big. We face threats like climate change, resource scarcity, and social conflicts. Therefore, we want solutions now. We seek answers immediately. The idea of going to another planet sometimes seems like an escape from these problems. A quick fix. It's called Plan B. On the other hand, there is the patience of the universe. The formation of stars takes millions of years. The evolution of planets stirs billions of years, and interstellar travel, if it is to be possible, is a project that could take centuries, even millennia. This requires a dedication not of a single generation, but of generations to come. How can a species with such urgent problems pursue a dream that requires so much patience? The tragic side of this question is that these two timescales conflict with each other. If we do not focus on today's urgent problems, we may not have a future in which to dream tomorrow's big dreams. The question of whether to spend our resources and energy to survive or to explore is one of our civilization's greatest moral dilemmas. But within this contradiction lies our greatest hope. Because the dream of going to the stars teaches us to think more long-term. It shows us how our actions today will affect generations hundreds of years from now. Building a starship is not just an engineering project, it is a project to build a more sustainable, more cooperative, and more patient civilization. Because a civilization that can go to the stars must first be a civilization that has learned to live in peace on its own planet. You are a part of this contrast. You, too, every day, try to strike a balance between the urgency of your immediate desires and the patience of your long-term goals. And your ability to strike this balance shapes not only your own future, but also the future of the world around you. Second, we encounter the contrast of sacrifice and legacy. On one hand, there is the immense sacrifice required by an interstellar journey. This is not just a financial cost, it is a human cost. The travelers leave behind their loved ones, their homes, and the only world they have ever known. On a relativistic journey, they renounce their own time and their own history. This is the greatest sacrifice an individual can make for the rest of the species. On the other hand, there is the incredible legacy created by this sacrifice. The first humans to step on the moon took that step not just for themselves, but for all humanity. Their journey inspired millions of people for generations. The first people to go to another star on a starship will not just discover a new world, they will redraw the boundaries of human potential. Their story will be etched into the collective memory of humanity and will forever remain a symbol of hope and courage. How can the greatest personal loss also become the greatest collective gain? The tragic side of this question is that those who make the sacrifice will never see the full impact of the legacy they create. The travelers may never know how great their impact was on Earth. They are like seeds planted for the future, and they remain under the ground without seeing what kind of tree that seed will become. But within this sacrifice lies the most immortal beauty, because leaving a legacy is a way to transcend the limits of our own biological lifespan. Through the things we do, the words we say, and the lives we touch, we continue to live long after we're gone. And going to a star on behalf of humanity is the greatest legacy one can leave. It is not just a discovery, but a gift to future generations, a gift that says, we were here, we accomplished this, and for you too, anything is possible. You are a part of this contrast. You, Jasasa, too, every day, make choices between your own comfort and helping others, and every small sacrifice you make leaves a small legacy in the world around you. Because the most meaningful lives are not just the ones we live for ourselves, but also the ones we leave behind for others. These final philosophical layers, patience, sacrifice, and legacy, show us the ultimate purpose of the journey. It is not just about going, it is about why we go. And that why is what brings us together, what forces us to be better, and what gives us hope even in the darkest moments. We now know that a human lifetime is tiny in the face of the universe's vastness, fleeting in the face of time's infinity, and lonely in the face of cosmic silence. But we also know that that small life can understand the universe. That fleeting moment can give meaning to the universe, and that lonely traveler can carry the hopes of all humanity. We have come to the end of this journey. We have brought together all these technical details, epic moments, and philosophical thoughts. Now we are ready to answer this great question, in all its complexity and beauty, and therefore, at the end of this entire journey, that final answer is much more than a number or a distance. On this journey, we question the limits of a human lifetime. We move from the ruthless equations of technology to the fragile walls of biology, and from there to the deepest secrets of physics and the most personal questions of philosophy. This was the story not only of how far we can go in space, but also of how deep that journey can take us inside. We now know that a human lifetime, with our current technology, can take us to the moon, and perhaps, with great difficulty, to Mars. But to reach the stars, we need not only faster engines, but also a more patient, wiser, and more unified civilization. Because the 4.25 light-year distance to the nearest star, Proxima Centauri, is not just a geographical barrier, it is a civilizational filter. To pass this filter requires mastering energy, biology, and time itself, and you are a part of this grand story. Because the journey to the stars is the collective dream not just of a select few astronauts, but of all humanity. You, too. Every time you look at the sky, you ask that ancient question, and the very act of asking that question is part of the answer, because it is proof of our curiosity, our desire to learn, and our effort to understand our place in the universe. If this journey has filled you with a sense of wonder and awe, like, subscribe, and comment to share these thoughts, because this conversation only gains meaning when we have it together. And in this journey, We spoke of the limits of a lifetime, which are the limits of time. But time itself had a beginning, and what came before that beginning is the greatest mystery of the universe. We spoke of the limits of a human lifetime. But I didn't tell you something. What if time itself has a limit? Science tells us the universe began with a Big Bang about 13.8 billion years ago. So what about before that moment? What was there? Before that time zero. In our next journey, we will look beyond the beginning of time. We begin